This research centre is composed of 3 research groups with different specialised fields of a chemical engineering, a materials science and an environmental engineering. Collaborations between the 3 research groups facilitate the world's most advanced research on hydrogen and energy carriers using ammonia. Ammonia Synthesis Group. Based on the chemical engineering approach, membrane separation research has been carried out to synthesize CO2-free hydrogen, which is a raw material for ammonia, from water using solar heat. Ammonia Storage Materials Group. Based on the materials science approach, R&D on high-purity hydrogen production from ammonia decomposition gas and leaked ammonia removal technology have been carried out. Safety Evaluation Group. Based on the environmental engineering approach, the safety of hydrogen and energy carriers during production, storage, transportation and utilization has been evaluated.
In order to mitigate extreme weather due to greenhouse gas emissions, China is now aiming toward a decarbonized society by 2060. EU is also aiming for this by 2050. Recently, Japanese Prime Minister Suga made a policy speech mentioning Japan is aiming toward a decarbonized society by 2050. Renewable energy is essential to achieve this decarbonized society. We have renewable energies such as solar power, wind power, hydropower, geothermal, solar thermal. Electricity is generated from these renewable energies. But these renewable energies are fluctuating. To stabilize the fluctuation, we need energy storage such as hydrogen storage materials. We have researched many kinds of hydrogen storage materials for more than 20 years. These materials are classified into 4 categories. First one, hydrogen storage alloys. Second one, inorganic chemical hydrolytes. Third one, carbon materials. Fourth one, liquid hydrolytes. First of all, thermodynamic analysis of these hydrogen storage materials was carried out. Based on this, we have evaluated and characterized 200 kinds of hydrogen storage materials. This figure shows hydrogen densities of hydrogen storage materials. The hydrogen densities of ammonia exist in this position. The volumetric density of ammonia is 1.5 times of liquid hydrogen. The gravimetric density is also large, and ammonia is also burnable, and ammonia can be used as an energy carrier for direct combustion. So we discovered this for the first time in the world. Then we joined energy carrier project in Japan. After that, we proposed establishing a research center for nitrogen recycling energy carrier at Hiroshima University. This proposal was accepted and related research has been carried out. This center is composed of 3 groups. First, ammonia synthesis group. Second, ammonia storage materials group. Third, ammonia safety evaluation group. Among these groups, I will show the research results of ammonia storage groups. This table shows the specification of hydrogen fuel for fuel cell vehicle. Purity of hydrogen is above 99.97%. The concentration of nitrogen with argon is below 100 ppm and ammonia is below 0.1 ppm. We need high purity hydrogen from ammonia decomposed gas. For this purpose, we focused on ammonia storage materials such as metal halide, borohydride, proton-based materials, ammonia borane, ammonium hydrogen sulfate, zeolite, and porous carbon. Thermodynamic analysis of ammonia storage materials was carried out using the equipment such as Belsop Max and Belsop HP Next as shown here. Then we have evaluated and characterized several dozen kinds of ammonia storage materials. We also carried out molecular dynamic simulation and observed the shape change by ammonia absorption. then obtain the following R&D guidelines. First one, large electronegativity of cation. Second one, polar structure. Third one, large pore volume. Based on this, we used lithium X type zeolite as the ammonia storage material for hydrogen purification. This figure shows pressure composition isotope of lithium X zeolite. X-axis is ammonia capacity and Y-axis is ammonia vapor pressure. The ammonia adsorption capacity is 5%, although ammonia vapor pressure is 80 ppm and large compared with the target value of 0.1 ppm. This suggests threshold of static adsorption method exists. Instead of the static adsorption method, the dynamic adsorption method was used to remove ammonia. This shows conceptual picture of specially designed breakthrough testing apparatus based on dynamic adsorption method and FTIR gas cell. Simulated ammonia decomposed gas is passed through the zeolite packed column, and exit ammonia concentration was detected by FTIR gas cell. Unfortunately, minimum detected ammonia concentration is above 0.1 ppm. So, we focused on an ammonia detector using wavelength scanned cavity ring down spectroscopy, WSCRDS. And exit ammonia concentration was detected by CRDS. CRDS is a reliable technique to measure trace ammonia in gases even at ppb level. This figure shows residual ammonia concentration passed through the zeolite packed column. Residual ammonia concentration is 0.01 to 0.02 ppm. Ammonia concentration sufficiently satisfies the hydrogen fuel specification. The dynamic adsorption capacity is 5.78% and similar to the static value. Ammonia is a toxic substance. All of the ammonia accidents are caused by the leakage from burn pipe and flange. We proposed new ammonia removal system. This shows conceptual picture of the new ammonia removal system. Water collects leaked ammonia. Then ammonia moves to insoluble proton-based material. Then ammonia and the material react together to form insoluble ammonium ion-based materials. The ammonia removal system combined water and insoluble proton-based materials will be candidate to reduce ammonia concentration in the atmosphere by suppression of water pollution. This shows the experimental results. Ammonia concentration decreases from 1000 ppm to 380 ppm using water. Then ammonia concentration drastically decreases from 1000 ppm to 0.5 ppm using a proposed new removal system containing water and proton-based material such as zirconium phosphate, because ammonia density is 9.4% and the plateau ammonia concentration is below 1 ppm. Therefore, the safety of ammonia can be improved using the new system. For global leveling of renewable energy, ammonia will be used for storage and transportation. For local leveling, energy storage systems such as battery will be used. Then the best mix of electricity, hydrogen, and heat will be required to realize a decarbonized society. I hope young people with science will research energy storage materials to realize decarbonized society.
It is well known that the hydrogen storage process of hydrogen storage materials is exothermic reaction, especially for alloys. They can literally produce a lot of heat in a very short time. And Besides, the endothermic desorption of hydrogen can be seen as the heat storage process. That's why we call them heat storage materials. This kind of feature is usually used for thermodynamical cycles such as heat pumps. And recently, we've been thinking about a new method to take advantage of this feature, which is to use it for accelerating chemical reaction. The application is also very simple and quick. Just apply hydrogen with appropriate pressure to the materials, and the generated heat will provide propulsion for chemical reaction. For example, exothermic reaction like ammonia synthesis, which requires high pressure hydrogen atmosphere and a large amount of heat.